Okay. Everything is okay. Hopefully. Today I'm not using the projector, so or maybe I will use it in the next 2 hours, not now. They told me that the wood yesterday and the wood today it worked, so I'm sure that when I will start it, it will not work. But anyway, let's start now at the blackboard, and I would like to continue on the issue of infiltration models. You remember yesterday we dealt with the derivation of the Richard equation. By the way, I didn't have time yesterday, please accept my apologies. I didn't have time to put online the couple of pages that I promised you to make available. I will do it later. I put the videos, but not the 2 pages describing the blueprint, the derivation of the Richard equation. Again, I will do it later today, and so you are done for that. Then we turn to simplified models, and we talked about the orthogonal infiltration model. Now I would like to deal with another simplified model, which is, I would say, simpler, even simpler than the orthogonal model, let's say, at least from an applied point of view. The model that I will introduce now is very much important, is very much applied because of the easiness of related to the application of this model. And therefore I think it is a very important approach. Probably you already know it because you know its importance, and in view of the fact that it's frequently applied, is often dealt with during basic hydrology courses. So maybe that you already know it, but it's not a problem. And the model is called SCS-CN. This is the acronym, infiltration model. And the meaning of the acronym, again is SCS stands for Soil Conservation Service. It's a governmental service of the US, United States, and CN stands for carbon number. And so the meaning of the terminology is very easy to understand. Soil Conservation Service is the governmental service in the United States who proposed this model, and the model was in particular called carbon number. You will understand better why. Okay? And now, the model was proposed first in 1972 with reference to the United States, because you will see it's an empirical model, and empirical coefficients are embedded in the model, and values for these coefficients were given with reference to the United States. But then, in view of the simplicity of the model, it started to become applied worldwide, and therefore in many countries were proposed adaptations of the model to the particular geographical context. Therefore, the literature proposed many contributions related to this model, mainly based on, again, adapting the model to given geographical contexts. So if you Google for SCS-CN, you would find, if you Googled, you would find several contributions, because, as I said, the model was subsequently modified in order to make it more detailed and adapted. I'm now introducing the original formulation. It didn't change much, actually. What changed are empirical value of the coefficient and some minor modifications, so you are not losing anything if I I talked to you the original version, but please be aware that there are a lot of contributions. Okay, so this is, as I said, a simplified model, and it's based on a very simple schematization that now I am introducing. And the schematization is based on a relationship between the cumulative precipitation, capital P, from the beginning of a rainfall event. Again, this is cumulative precipitation, cumulative rainfall. And at the numerator we have the cumulative surface runoff. So cumulative, let's say, net rainfall. Of course, Q is lower than P, because Q is, again, the contribution to the surface runoff, while P, of course, is gross Lorda precipitation. Okay? This ratio is equated to another ratio, F over S, where F is cumulative infiltration from the beginning of the event, and S is maximum soil water storage. It's something similar to Cmax of the Helmut model. It's soil water, maximum water storage, or you can call it maximum infiltration capacity of the soil. It's S means the maximum amount of water that can be stored in the soil. Usually, these quantities here are expressed in terms of length. So cumulative precipitation, cumulative surface runoff, cumulative infiltration, and the maximum storage. The unit of measure is length. So it's a volume per unit area. And to be more precise, I should highlight here the dependence on time of Q, P, and F. I'm not highlighting dependence on time just to make the symbology simpler. But this quantity, of course, cumulative contribution to surface runoff, cumulative precipitation, and cumulative infiltration from the beginning of the event, they depend on time, of course, while S does not depend on time. This is a fixed quantity. Our objective here is to compute Q. So what you see from this relationship, this is quite intuitive. What you see is that when the cumulative infiltration equates the maximum water storage of the soil, so when the soil is saturated, you get that the equivalence between the contribution to surface runoff and precipitation. Indeed, you never reach saturation according to this method, because you see that you get it only asymptotically, because infiltration, the contribution to infiltration decreases as F approaches S. When F becomes very close to S, you have the contribution to infiltration, so the contribution to F, that is progressively decreasing. So only asymptotically you get saturation here. Okay, but here you have two unknowns, which are, let's forget about S for now. Let's assume that we can estimate S, because it's a soil storage capacity, so it's a behavior of the soil. Let's assume that we can estimate it, so it's not an unknown. We will see later how to estimate it. It's an empirical estimation. I will explain later. But even if we admit that we knew S, and we of course know P, which is precipitation, but still we would have two unknowns, which are Q and F, which are cumulative contribution again to surface runoff and cumulative infiltration. And so we need a second relationship. The second relationship is quite simple. We can write that, that F is equal to P minus Q. This is a continuity equation, it's a mass balance equation. Infiltration is equal to gross rainfall minus the contribution to surface runoff. And therefore you can write, okay, we can take it as it is. Now we can combine these two equations to eliminate an unknown, to eliminate F. Given that we are interested in computing Q, let's eliminate F. So we can write that Q over P is equal to P minus Q over S. So we can rearrange this equation by writing Qs is equal to P that multiplies P minus Q, or P squared minus PQ. Now let's bring to the left-hand side the two terms that include Q. So we have Qs plus PQ is equal to P squared. Now we can write that Q, which multiplies S plus P, is equal to P squared, and therefore we can derive Q as the ratio between P squared at the numerator and P plus S at the denominator. Okay, of course we still have some issues to solve, to deal with, and the first issue is related to the estimation of S, because we have rainfall but we don't have S. And also there is another issue that I'm now introducing, which is related to what is called initial abstraction that takes into account interception. Now let me introduce what interception is. It's something that you already know. Interception is operated by vegetation, trees, grass. At the beginning of the event, vegetation keeps a part of rainfall, which is kept by leaves or by the grass. It's a part of precipitation that doesn't reach the soil. We all know that at the beginning of a rainfall event, if we want to get repair, we can go under a tree if it's not a thunderstorm, because you know that it's dangerous for thunders. But if you go under the leaves of a tree, you know that you don't get any rain for some time. But you also know that after some time you start getting rain, because leaves are saturated, interception is finished, and the rain starts falling on the ground. This is a very complex process, which is studied in many experiments. It's still studied in order to understand it. We will not deal with it in detail, but I would like to make clear that it's a very complex process, because it has been proved that part of the rainfall is kept not just by the leaves, but also by the wood parts of the trees. And it has been observed, for instance, that after some time, we can observe some flow of water flowing along, I don't know how to say in English, tronco in Italian, and the branches. You can observe some water flow along the branches, rami, and along the, I don't remember the name of tronco, but anyway, I will tell you maybe later on. And so there is this type of flux, there is this type of retention operated by the wood part of the trees, which is associated with the retention, the water retention operated by the leaves. And the amount of water that is kept by the leaves and again the wood parts of the tree are strictly dependent on the type of vegetation and also the season. Of course, you can understand that during winter interception is less pronounced because you don't have leaves for some type of vegetation. But even in different phases of the active vegetation season, you have a different level of interception because when the leaves are very young, they can keep more water because they are strong. While in proximity of the autumn, leaves get weaker and they cannot keep as much water as during the very active vegetation season. So it's a very complex process, and people, I have maybe later on I can show you some pictures. People try to estimate the rainfall under the trees by making experiments in comparison with rainfall in open fields. And they try to compare, to understand how interception works. It's a very complicated process. And this is not infiltration. This is something that is causing a loss of rainfall, because you know, after the rainfall event, the water is still kept by leaves and by the trees and is subsequently evaporated. So it's a rainfall loss, which is not due to infiltration, it's a different process. And it's quite important. It has been proved that it's quite important, not as important as some years ago people in the media wanted to prove. I mean, there has been a period some years ago during which we experienced some floods in Italy. In particular, two floods on the Po River in 1994 and 2000, and therefore there was the belief at that time that flood frequency was increasing in Italy. After 2000 we didn't get any major flood. We get flood in small rivers, but not in the Po River. We didn't get any major flood after the year 2000. So at that time, anyway, people got convinced that the flood frequency was increasing, and the media for in many instances, they supported a theory, a belief that it was the reduction in vegetation over the Po River basin that was increasing, the reduction of vegetated areas that was increasing the flood frequency. Actually, vegetation is not so influential in the Po River basin. This has been proved later on. And the changes in vegetation, changes in land cover has not been so influential on floods. It's important interception. It's important evapotranspiration, but not as much as to be able to heavily affect flood frequency in a so complex and so huge river basin. But anyway, let's go back to our issue. We have to take into account interception here, and this model, interception, for instance, is not taken into account explicitly by the ortho model. In this model, interception is explicitly taken into account. And the way in which it's taken into account is very simple. We substitute to rainfall, to P, the quantity P minus initial abstraction, IA. So there is an initial fraction of rainfall that is subtracted. Therefore, this relationship becomes Q equal P minus IA squared divided by P minus IA plus S. This is the classical formulation of the SCN model, which takes into account interception in this way. Of course, we still have to see how IA is computed. Okay. Now, what is the value of IA? The method proposes a very simple approach to determine IA, which is equated to a fraction of S, and the original version proposes to use 20%, namely the original method assumes that 20% of the maximum soil water storage is the amount of the initial obstruction. It means that a rainfall event, to be able to trigger some Q, some surface runoff, must exceed the quantity 0.2 times S. Okay, so we can change it here. We can include the relationship on the left in this equation, and then I can write Q is equal to P minus 0.2 S squared divided by P plus 0.8 S, because it's P plus S minus 0.2 S, so the result at the denominator is P plus 0.8 S. Okay, now the only problem is to estimate S. The SCS proposes this relationship to estimate S. S is equal to 254, 100 divided Cn minus 1. This is in millimeters. This is an empirical relationship to estimate S, and it's obtained in this way. The quantity, the coefficient 254 is related to the use of inches instead of the international system in the United States. So they defined the empirical relationship without this coefficient because they wanted to obtain the S in a different unit measure. To convert it to the international system, we have to introduce this. This is the explanation for this coefficient. And the result is expressed in millimeters again. And here you can see one more parameter, which is called Cn. This parameter is called Carpe number, numero di curva in Italian. And it's a parameter that only depends on soil type and soil use. So land use and soil type. Cn is varying between 0 minus Cn minus 100, where 0 means impervious soil. Sorry, 100 means impervious soil. In fact, if you see here, if you substitute 100 for Cn, you obtain 1 minus 1, which is 0. So S assumes the value of 0. So Cn equal to 100, once again, means impervious soil. We can put an equal sign here, because indeed, if you have impervious soils like paved roads, like roofs, you have to put Cn equal 100. And the lower limit for Cn is 0, and you see what happens for Cn tending to 0. The quantity between parentheses tends to infinity, and therefore you get an infinite value for S. So you don't reach 0 because it's not possible, otherwise it's not defined, this relationship. But as you approach 0, you get increasing values for S, which tends to infinity, for Cn tending to 0. So it's quite clear that the Cn value depends on the infiltration capacity of the soil, and therefore depends on the soil behaviors. And in particular, the SCN suggested that Cn depends on soil type and land use, or land cover. Soil type is basically different with respect to land use. They are related. Because if you have a very permeable soil, a soil that can store a lot of water, it's more likely for this soil to have a vegetation cover, a very rigorous vegetation cover. Because if the soil can keep a lot of water, of course vegetation is more happy, and therefore it's easier for the vegetation to colonize this type of soil. Instead, if you have a soil that is close to impervious, it's difficult for the vegetation to colonize it, because there is no water in the soil. Therefore, they are related, but they are different. And of course, because even if the soil is permeable, of course, the human influence can change the land cover. And therefore, they are both affecting infiltration, but they are different behaviors. So what the SCN proposed is to identify 4 types of soil behavior, which they called soil types A, B, C, and D. So soil types, and these are 4, which are called A, B, C, and D. And it's a very gross distinction, gross meaning a rough distinction. You have just 4 categories, and it's quite easy to place the soil, the considered soil, within these categories, because definition is like it's basically a porosity distinction, so you can really easily identify where to put your soil category. When I turn the computer on, we can look on the web to search for the definition of the soil categories. You will see that it's very easy to place a considered soil in the respective category. And then for each soil type, they identified a very wide, several alternatives for the soil cover. So rigorous vegetation instead of grass, instead of cultivated lands, instead of urban areas, and the description is very detailed, and there are several options in this case. And for each soil land use option and each soil option, the SCS provided tables of the CN coefficient. We can see an example later on. So these are very simple tables. You enter into the table, again, with the soil type and the land cover type, and you get an indication of the CN coefficient. Of course, these tables were calibrated for the United States, as I mentioned at the beginning of my lecture, and therefore there is a potential problem to check if the CN values are appropriate for a different geographical context, because they made experiments to determine the CN value. They measured the soil storage capacity, and then estimated the CN value. So they made a real experiment, actual experiment. Of course, this depends on the geographical context. And a potential problem is when you refer to wide areas. Because if you refer to a very specific location, which is very small, like your garden, it's easy for you to estimate what type of soil you have in your garden and what type of vegetation cover. It's very easy. But if you think about a catchment, then you have to provide an average estimate. Because if you look around in a catchment, you see many different situations. You see rocks, which means impervious soil. You see cultivated areas, which means permeable soil, but also a different land cover. So you have to make an estimate. And what is usually done in practical application is to try to subdivide the catchment in homogeneous areas from the point of view of at least land cover. And you can safely assume that for similar land covers you have similar soil behaviors. And therefore, you estimate the CN for any homogeneous area and then you take the average, a weighted average, where the weight is given by the fraction of the catchment area that is covered by each considered homogeneous surface. So if you have a catchment of 100 square kilometers of extension and you have 10 square kilometers covered by cultivated areas, you estimate the CN, and when computing the average, you use a weight of 1 over 10, 10 over 100, 1 over 10. Okay? This is the approach that is usually applied. It's not easy because when you deal with a large catchment, to identify homogeneous area is not easy, and also you should take into account the exposure, because it has been proved that infiltration is different depending on the exposure of the catchment. And with different exposures, you get different vegetation, so you can partially take the change in exposure into account when assessing the land cover, but still, even for homogeneous land covers, and I would say also homogeneous soils, if you change the exposure or you change the slope, you get changes. So sometimes you have to provide your interpretation, like you see very similar slopes, but the slope of the slopes is different. It may be safer to increase the CN number if the slope is very tilted. Okay, so it's an evaluation that is not easy, but there is to say that even for Italy, several studies have been performed to estimate the CN number for significant catchments. For instance, for the Po River, there are estimates of the CN coefficient for significant subbasins and also for the whole Po River basin. There are several studies presented by the literature on the computation of the CN coefficient. Okay, so once that you obtain an estimate of the CN coefficient, you can compute S, and then it's very easy to use this equation to compute, depending on cumulative rainfall, to compute the cumulative contribution to surface runoff, to river discharge. Okay, here you can see that the model is potentially simple. You can see some relevant features. For instance, you don't see any account for evapotranspiration here. It means that this is an event-based model. It cannot simulate the dry-up process that is taking place during the dry periods. However, in principle, it's very easy to modify this model to take evapotranspiration into account. What you should do is just change. I deleted the first equation, but you should change the value of F by allowing it to decrease depending on evapotranspiration. So you should go back to the first equation, and you should not eliminate F, keep it, and allow it to change in order to account for evapotranspiration. This means that you cannot couple the two equations to eliminate F, because we cannot find F anymore here because I coupled the two equations, the two starting equations, to eliminate it. You cannot do that, so you cannot derive a compact relationship. You should keep the two equations, but numerically you can solve that, because at each time step you increase F for the contribution due to precipitation, and you decrease F by subtracting the contribution of evapotranspiration. And then once that you have updated the F value, you can compute Q. And in fact, the literature presents a lot of contributions regarding modification of the Gardner-Amber method to make it able to simulate the dry up of the soil during interstorm periods, the period of time between the end of a storm and the beginning of the subsequent one. So you get a lot of contributions to adapt it. We are not going into the details because basically it's an empirical knowledge. If you use a finely different solution, it's very easy to adapt it. So this is the first issue to mention. And also there is a second issue to mention. People using this model